The Bosanquet equation allows the estimation of the self-diffusivity in a porous material by combining the Knudsen prescription to describe the contributions due to molecule wall collisions and the kinetic gas theory to describe the diffusivity contributions due to molecule collisions. The Bosanquet formula is laid out in a report published in 1944. For further background information, I refer you to my papers in Chemical Engineering Science 2012 and in Industrial Engineering Chemistry Research 2016. In this presentation, I will do three things. I will use firstly MD simulations to test the validity of the Knudsen prescription. Thereafter, I will use MD simulation to test the accuracy of the kinetic gas theory to describe diffusivity of unary guest molecules. And thirdly, we will test the Bosanquet formula by examining MD simulation data for diffusivity of a variety of gas molecules inside mesopores. Watch also my presentations on investigating the validity of the Knudsen diffusivity prescription and also the presentation on the dusty gas model. These two presentations are available on my YouTube channel. The Knudsen diffusivity prescription for molecule wall collisions is given by this formula derived by Martin Hans Christian Knudsen, a Danish physicist. The Knudsen diffusivity is equal to the pore diameter divided by 3 times the square root of 8 times the gas constant R, temperature T by 3.14, and the molar mass. Remember, the units here are in SI units. The formula is applicable provided the gas molecule undergoes diffuse reflectance on striking the pore wall. It is not applicable, as we shall see later in this presentation, it's not applicable to components that absorb more strongly and have a bias to move along the wall. We look at diffusion of hydrogen inside a 4 nanometer mesopore. The hydrogen molecules collide with other hydrogen molecules. They also collide with the wall. On colliding with the wall, a hydrogen molecule gets reflected. We now look at the motion of methane molecules. There is a stark difference between the motion of methane molecules in comparison with the hydrogen molecules observed earlier. The methane molecules on colliding with the wall stick to it and have a tendency to move along the wall before returning to the bulk. So you see a higher concentration of methane near the pore wall surface because of stronger adsorption on the pore wall. So to differentiate between the characteristics of diffusion of hydrogen and methane, we look at the cartoon here. Hydrogen on colliding with the pore wall undergoes diffuse reflectance, which is a term that indicates that the angle of incidence bears no relation with the angle at which the molecule gets reflected. Methane molecule on colliding with the wall has a tendency to hop to a neighboring site before returning to the bulk gas phase. So there are fundamental differences between molecules that are poorly adsorbed and molecules that are strongly adsorbed. The MD data for diffusivity of methane in zeolites, MOPs, COFs, and silica channels with various pore dimensions are plotted here in red circles and green squares. The red circles are for silica mesopores, and the green squares are for the zeolites, MOPs, and COFs. The solid black line is the Knudsen diffusivity formula. Similarly, the MD data for argon is plotted here and compared with the Knudsen diffusivity formula. For both methane and argon, we see that the Knudsen diffusivity formula overestimates the diffusivity value when compared to the values determined from MD simulations. We take the ratio of the values determined from MD to the value calculated using the Knudsen formula and plot that ratio as a function of the Henry coefficient in this graph for a channel that is 3.4 nanometers. It's a COF called BTP COF. And we see that the deviations from the Knudsen formula becomes greater with increasing adsorption strength. This is because with increasing adsorption strength, there is a tendency for the gas molecules to deviate more strongly from the Knudsen prescription because of the biased nature of hops along the surface. The same is true for a 2 nanometer silica pore, where we see that the MD simulated values of the diffusivity reflecting molecule wall collisions deviates from the Knudsen formula to a greater extent with increased Henry coefficient. In other words, the more strongly adsorbed the molecule, the poorer is the agreement between the Knudsen prescription and the values determined from MD simulations. The takeaway message from this video presentation is that the Knudsen diffusivity formula is applicable for poorly adsorbed gas molecules, and with increased strength of adsorption, the deviation from the Knudsen formula increases. Further details are available in my publication from 2016. We now test the accuracy of the kinetic gas theory to predict the self-diffusivities of unary fluids: hydrogen, argon, CO2, methane, ethane, and propane. The symbols represent the MD data on the self-diffusivity plotted against the molar concentration of the unary gases in the units of kilomoles per cubic meter. For dilute gases with molar concentrations below about 10 kilomoles per cubic meter, the agreement of the kinetic gas theory to predict the diffusivity is very good. The formula I use is due to Fuller, Shetler, and Giddings, published in 1966. It's a slight modification of the kinetic gas theory using some empirical parameters. The accuracy is excellent for pressures below about 10 megapascals. Having now examined molecule wall collisions and the limitations of the Knudsen prescription, and molecule-molecule collisions and the applicability of the kinetic gas theory, we now proceed to examining the accuracy of the Bosanquet formula by performing MD simulations for a 3.4 nanometer mesoporous material at pores which are larger than 2 nanometers, for which both molecule wall collisions and molecule-molecule collisions are important. In this case, we perform MD simulations for a 3.4 nanometer covalent organic framework called BTP-COF. It has one-dimensional channels that are hexagonal in shape. This table provides some data on the crystalline structure. This gives you the dimensions of a unit cell. This is the framework density and the pore volume. Let's look at 4 molecules with increasing strength: hydrogen, argon, methane, and carbon dioxide, and see how these molecules traverse the pore. Hydrogen, as you might expect, since it's poorly adsorbed, doesn't remain on the surface and gets reflected and returns to the core region. Argon, which is most strongly adsorbed, has a tendency to remain on the surface and hop to a neighboring site before returning to the core region. And in the core region, it experiences molecule collisions. For methane, that has a higher adsorption strength than argon, there's a higher concentration of methane near the pore walls and a lower concentration of molecules in the core region as compared to argon. For carbon dioxide, most of the molecules are close to the surface and suffer a biased motion, and the bias being in favor of motion along the surface rather than colliding with the wall and returning to the core region. You see only a very small fraction of molecules have entered the core region and experiencing molecule-molecule collisions. So for these 4 guest molecules, let's compare the predictions of the Bosanquet formula that combines molecule wall collisions with molecule-molecule collisions. The Bosanquet formula is indicated by these crosses for hydrogen, argon, methane, and carbon dioxide. The Bosanquet formula is compared with the MD simulations shown by these red circles. For hydrogen, the agreement between the MD simulations and the Bosanquet formula is very good. And the agreement is significantly poorer for argon, but as the pore concentration increases, the x-axis plots the pore concentration in units of kilomoles of guest molecule per cubic meter of pore volume. As the pore concentration increases, the molecule collisions become of increasing importance, and since the molecule collisions are very well described by the kinetic gas theory, the agreement between MD simulations and the Bosanquet formula is very good for high concentrations, say beyond 10 kilomoles per cubic meter, and is poor at low concentrations because at these low concentrations the molecule wall collisions are important, and for argon, which has a finite adsorption strength, the Knudsen contribution to the Bosanquet formula is of insufficient accuracy. The story is identical to that of methane, where the agreement is poorer for low pore concentrations and becomes increasingly good. The Bosanquet formula becomes increasingly accurate as the pore concentration increases to say beyond 10 kilomoles per cubic meter. The accuracy of the Bosanquet formula for CO2 is significantly poorer than for methane because of the much stronger adsorption strength of CO2. That's about